All right, now I have this next example to show you how to perform a goodness of fit hypothesis test. But remember previously, what I shared is that your test statistic comes from your observed values and your expected values. And the expected values could be different depending on whether the probabilities of each outcome are equal or if the probabilities of each outcome are unequal. So what we're going to do in this example is we're going to run through almost like two examples simultaneously. One example will be an example of uniform probabilities, and right next to it will be an example of non-uniform probabilities. I think this will help illustrate what the difference is, where everything else is the same. So everything else will be the same. The one thing that'll stand out as being different is exactly what I'm trying to show here. Okay. So I think that that's probably going to be the best way to teach this. Okay. So let's learn how to apply a goodness of fit hypothesis test through parallel scenarios. All right. So we're going to look at trying to determine if a six-sided die is a fair die or not. So test the claim in which a six-sided die is considered fair with a 5% significance level. So 45 trials of a six-sided die were recorded. So a trial is just another word for a roll. So a six-sided die was rolled 45 times. The following frequency table was created. So you can see that a roll of 1 occurred 13 times. A roll of 2 occurred 6 times. 3, 12 times. 4, 9 times. 5, 3 times. 6, 2 times. Okay, so, you know, I'm trying to erase. I apologize for the delay here with my laptop. Here we go. All right, so you can see across the top, this is the outcome for the six-sided die across that top row. And the bottom row is the observed frequency. So these are our observed values. Okay, that's the variable O that I referenced earlier. Um, so let's start to take this apart and see what we've got. So we know we've got 45 trials. So that means we have a sample size of 45. Now notice there are what we would refer to as categories. So each of these outcomes are considered altogether. These are our categories. So there are 6 categories. All right. So what does this mean? All right. So the fact that there are 6 categories means, actually, let me put this over here where it'll be a little bit. Do this again. So we've got 6 categories, which means this variable k is equal to 6. And remember that degrees of freedom is equal to k minus 1, or 6 minus 1. So our degrees of freedom is going to be equal to 5. All right, so degrees of freedom is not sample size minus 1. It is the number of categories, or the number of outcomes minus 1 instead. All right. So what we've got here in this table, I've oriented this table horizontally, but if I were to turn this around and orient this vertically, where here you've got your six-sided die outcome of 1, 2, 3, 4, 5, and 6, then the next column would be frequency, right? And this would be 13, 6, 12, 9, 3, 2. And so what this actually looks like is a frequency distribution table, all right? Now, like I said, I'm going to be kind of solving two different scenarios simultaneously. So in the first scenario, okay, the claim is that the six-sided die is a fair die. Okay, a fair die means it hasn't been altered to cheat. Okay, and because it has not been altered to cheat, that means the probability of rolling a 1 is equal to the probability of rolling a 2, which is equal to the probability of rolling a 3, a 4, a 5, and a 6. So each of these has an equal probability of being rolled of 1 out of 6. And because we're claiming that this is a fair die, this is our original claim. And because we're claiming that all of these probabilities are equal, that is our null hypothesis. Now, the alternate hypothesis in this scenario is that at least one of the probabilities is significantly different. Another way of saying this is that it's therefore an unfair die, and maybe that's leading to cheating. Now, scenario 2, which we're going to do side by side, okay, is making the claim that the six-sided die is unfair. Okay, but we're not just saying it's just unfair, but it's unfair in a specific way. It's unfair such that the probability of rolling a 1 is 50%. And the probability of rolling any other number is 10%. So this die is unfair such that half the time, you're going to roll a 1. Sorry, you're going to roll a 1. And that is our original claim. That's our null hypothesis. The alternate hypothesis is that the probability is significantly different from the proposed distribution. So this die may be unfair. It just may not be unfair in this particular way. Okay, that's what the alternate hypothesis is saying. Okay, so again, we're using the same observed values, and we're doing two examples at the same time. All right. And that's what I have here on this next page. So here's scenario 1, where we have a frequency distribution table. And this is the scenario where we're assuming this is a fair die. And over here on this shaded side, this is scenario 2. And this is the scenario where we have an unfair die. Now, this scenario here where we have a fair die, this means that we've got uniform probabilities. All right. And what that means is that each outcome in our frequency distribution table has an equal probability of occurring. Right. So remember that on a six-sided dice, the probability of any one side coming up is 1/6. So that's why the probability on a fair die is uniform. Now, this O column, pardon me while I try and switch colors. Yeah, I know. Serenity now. Apologize for the wait. Okay. So these observed values, remember, out of 45 rolls of the die, a 1 came up 13 times, a 2 6 times, a 3 12 times, a 4 9 times, a 5 3 times, and a 6 2 times. Okay, so this is like an observed frequency. Um, Now let's see. So I don't want to go much further because I want you to remember that here the probabilities are all equal. Now let's flip over to the other scenario. So scenario two is that we've got an unfair die. Now once again, we still have the same number of trials, the same number of die rolls. We have the same observed frequency, right? A 1 came up 13 times, a 2 6 times, a 3 12 times, a 4 9 times, a 5 3 times, and a 6 2 times. All right, but what's different now is that the probabilities are not uniform. Here we go. So what we have is non-uniform probability. Okay, and so notice previously the probabilities were all equal, but our claim is that a 1 will come up 50% of the time and the rest will come up 10% of the time. So those are unequal probabilities. All right, you might say, well, most of them are equal. Yeah, but not all of them. One of them is 50%. One of them is different. Okay, so do you see the contrast and the difference between these two scenarios, these two examples? Because really, this is the only difference. Now, that difference will now percolate through both hypothesis tests, okay? But this is the significant thing to pay attention to, is whether the probabilities are unequal or if the probabilities are equal. Now, if the probabilities are equal, then this is how you're going to calculate the expected value. The expected value is just the sample size divided by the number of categories. So you can see I've got this other column here, which is the expected value, which is 45 divided by 6. And it's 45 divided by 6 all the way down. Okay. Now, at this point, let's go ahead and feed some of this information into our respective calculators here. Now, the NumWorks calculator functions a little bit differently. So I'm not going to be switching over to the NumWorks calculator just... No, I think I will. No, I think I will. Sorry, it's just hard keeping three calculators in my mind at once. Okay, how it's all going to work together at the same time. All right, so but first let's go with the Texas Instruments. So the first thing I did is, with the Texas Instruments, I'm in the list editor. Okay, so let me just quit out of this. So to get the list editor, hit the Stat button, go to Edit. Here we are. Now I'm using the first three lists for scenario one, and I'm using the last three lists for scenario two. So you can see here, list one, that's all of those equal probabilities that I had here, 0.167, right? And then list two are my observed values. So list two is my observed values. And then list three I've left blank because I want to put the expected values in that list. Okay, now I am doing a little bit more, I'm showing more than I did down below with my screenshots, but it's because I think it's going to be important for you right now to see these probabilities next to the numbers. All right, list four is the probabilities in our second scenario. List five are the observed values. Okay, it's the same as here. And then list six is going to be the expected values that we'll calculate. Okay. So let me show you also on the Texas Instruments 83. Okay, if you're using an older calculator. So again, let me turn this on. Kind of funny to turn it on a computer emulator. Hello. There we go. Um, so, you get to the list editor the same way, stat button, edit, and I've arranged it the same way. It's just that the screen on the Texas Instruments 83 is a little smaller, so you can't see as many columns as you can on the newer models. But still, list one are the equal probabilities, list two are the observed values, list three will be the expected values. This is for the first scenario. And if I keep scrolling to the right, here's the unequal probabilities, here's the observed values, and then this will be the expected values for the second scenario. Okay. So that's how I got this set up. And on the NumWorks calculator, what I've done is I haven't set up the equal probability. Okay, and I'll explain why. What I have done though is I've gone into the regression app. Okay, this regression app, and I put the unequal probabilities in X1 and the observed values in Y1. Okay, and I think in a moment you'll see why I set it up that way. Okay, so let's come back. So what we want to do is we want to have a list of our expected values. So to calculate the expected values where the probabilities are uniform, it's just going to be 45 divided by 6. Okay. So over here, I'm just going to come over to list 3, which is my list of expected values here when the probabilities are uniform. And I'm just going to put 45 divided by 6. Right? 45 divided by 6. Now this turns out to come out exactly to 7.5. So I could just type 7.5. But, if you weren't sure, or if it comes out to a really messy fraction or decimal point, then just put in the fraction and let the calculator do the work for you, right? Do something like that. And you can do the same thing, here, sorry, with the TI-83. So I'll come over here to list 3 and I'll come down to the first row. And then if I put 45 divided by 6, right, it works the same way. So I'm going to put the expected value all the way down. Just like that. All right. Now, why did I not do that here? The reason why I didn't do it here is um, because of the way the NumWorks calculator works a little bit differently. Instead, what I would do is I would come out and just go to the calculation. No, I wouldn't even do that. Okay. Instead, sorry, let's just go to the Inferences app, go to Tests, go to chi-squared test, do goodness of fit, because that's what we're doing. And you see, this is the reason why I'm having some difficulty here trying to merge the two calculators. The NumWorks calculator wants you to put the observed and the expected values within this function. It doesn't allow you to put those values in a table somewhere else and then refer to them in this function. Okay. So what we have to do here is we actually have to put these expected values. So here is where you'd put like 45 divided by 6. Okay. Or just type it in every time like that. Okay, just like that. All right, but let's take a step back and let's see what this is actually trying to tell us. All right. What this is trying to tell us is that with this six-sided die, if it was truly fair and has an equal probability of every outcome occurring, what we would expect is that a one would come up 7.5 times out of 45, that a two would come up 7.5 times out of 45 die rolls. A three would come up, right? So each of these outcomes should have a frequency that's equal. Now we can see it doesn't appear that that's the case. It looks like a one came up and a three came up more times than anything else, right? But what the expected value is saying, because the probabilities are equal, we would expect each outcome to have an equal frequency. That's what the expected values are. All right. Now, by contrast, over here in scenario two, we have a non-uniform probability scenario. So the probabilities are all different. So how do we calculate expected values when the probabilities are different? Well, we take our sample size and we multiply it times each probability. And this is why I've done this in the calculator. Okay. So we want to do sample size times probability. So how did I get 22.5, 4.5, 4.5, and so on? Let me show you. So remember here, lists 4, 5, and 6. Okay, these are my non-uniform probability scenario. So list 6 is going to be composed of, so I want to make sure now, instead of just typing in the numbers, I want to program it. So I want to have list 6 selected, and this is going to be my sample size times the list of probabilities. So times list 4. And this is where I get 22.5 and the rest are 4.5. 22.5 and the rest are 4.5. All right. Let me do the same thing with the TI-83. So again, I can click to the right and I went ahead and put those values in. So I want to have list 6 selected. This is going to be my sample size times my probabilities, which are in list 4. And then I can hit enter. And see, it gives me 22.5, 4.5, 4.5, 4.5. All right. So now I'm going to come back to the numworks calculator. All right. Now we're going to have to like run this function twice. Okay. But let me show you how you could use the calculator to calculate those values for you. Okay. So I'm going to go back home. I'm going to go back to the regression app. And here's where I put those unequal probabilities. Here's my observed values. So this column X2, I'm going to click OK. I'm going to fill this with a formula. You put empty. And I'm going to make X2 going to be equal to my sample size times my probabilities, which is X1. So shift alpha, then the 2 key, that'll print an X, 1. And there's my 22.5 and all my 4.5s. Now, unfortunately, I think I'm going to have to type these in. Okay. So this is an example where the numworks is a little clunky. All right. But at the very least, here you can use the regression app to kind of calculate all of these values quickly for you. All right. So, um, again, the expected value column is the frequency that we would expect each of these outcomes to occur. So clearly we can kind of see that if the die was fair, you know, we would expect each outcome to occur the same with the same frequency, and that's not happening. So it doesn't look like our die is fair. Okay, but we have to prove this statistically. Okay, but qualitatively, it's looking like it's not a fair die to begin with. Now, here, scenario two, we're proposing, we're claiming it's unfair, but it's unfair in a certain way. We're saying it's unfair that one will occur half of the time. And if one occurs half the time, then out of 45 die rolls, we would expect it to occur 22.5 times, and everything else 4.5 times. Well, it already looks like our die is unfair, but it's just not unfair this way, right? Maybe, the probability of one occurring is maybe 30% of the time and 30% of the time, and the rest is 0.1. That might be a worthwhile one to try. Um, but at least it's not unfair in this particular scenario. All right. So that's how we complete the expected values using these two formulas here, given these two different scenarios where the probabilities are equal and the probabilities are unequal. Now, just so you are aware of what your calculator is doing, in the past, I had my students kind of calculate these other columns and calculate a test statistic, but we'll just use the calculator to do the heavy lifting. But basically what's happening is what your calculator is doing is it's taking the observed and the expected and it's subtracting them. Okay, then it's taking this observed minus expected difference, it's squaring it and dividing it by the expected again and getting this column of values. And the test statistic is just the sum of this column. So if you were to add all these up, it'd come out to 14.07. And it's just using the same algorithm over here. So this column is observed minus expected. This column is it takes that observed minus expected difference, it squares it and divides by the expected, and you get all of these values. And the test statistic is just the sum of all of those. That's what this little mathematical sigma here, this is capital sigma, I believe. That's what this symbol means, the sum of all of these. So the sum of all of these, and that comes out to a test statistic of 23.4. Okay, but let's see how we actually get that on our calculators. All right. So this is where we use a goodness of fit test. So first, let's use the modern Texas Instruments. So what we need is our list of, we'll do the first scenario. We need our list of observed values and expected. So my observed values are in list 2, my expected are in list 3. So I need to remember that. So I'm going to come over here to stat, go to tests, and I'm going to scroll up once because I know this is towards the bottom. Okay, so you see it says chi-squared goodness of fit test. So I'm going to hit enter. Now this function is missing on the Texas Instruments 83 model. Okay, if you look for it there, you won't find it. So the list of observed values is in list 2. The list of expected values that we calculated, that was list 3. And the degrees of freedom was the number of categories minus 1. So we had 6 categories or 6 outcomes, different outcomes, unique outcomes, minus 1. So that should be a 5. Okay. Now I'm going to leave this up because I want to show kind of like the similarities with my program. So if we come over here to Texas Instruments 83, again, let me scroll over. Again, I've made it identical. So our observed are in list 2 and our expected are in list 3. So let me just show you that this goodness of fit test is not there. So if I scroll down and I keep scrolling down, we're looking for a chi-squared goodness of fit. Now on the newer modern one, it was right here. And you can see it's not there. Okay. Yeah, so it's just not there. So if we go to program and scroll down, okay, one of the programs that I wrote is this one, chi-squared goodness of fit 83. So hit enter twice. Okay, it wants the list of observed values. Okay, just like here. So we're going to put list 2, enter. Then it wants the list, the expected value list. Okay, that's going to be list 3. So we'll put that in. And it already calculates the degrees of freedom for you. So you don't even have to put that in. Okay, but let me come back over to the new model. And let me put the old model up. And you'll see the first value is our test statistic, right? Our test statistic, which is 14.07 roughly, 14.07. The p-value is 0.01519. The next value is the p-value, that's 0.01519. Okay, degrees of freedom 5, degrees of freedom 5. All right. Now on the NumWorks calculator, we need to go back to the inference app. Click OK. Now so here we've got observed, here we have our expected. And I think it changed the degrees of freedom as I was putting in these values. So I don't think that's something that you'll have to worry about typing in, but just be ready to do that. And I think on this one, we are doing this with a 5% significance level. Okay, so we want to have that. Scroll down, we'll click next. Okay, and there's our chi-squared test statistic and our p-value. Okay, same values that we got over here with the Texas Instruments. Now, if we come back to this problem, you can see here on this screenshot, I've got the test statistic of 14.07 and the p-value of 0.015. And here's the NumWorks screenshot of that. Okay, now if I go through those same steps, but instead I do it with, I think this is list 5 and list 6. All right, then I'm going to get different test statistic and p-values. All right. So I guess, yeah, let's just go ahead and do that. You can maybe skip forward on the video, if you're like, yeah, I get it. But I just want to make sure everybody sees this. So let me go back to my list editor just to show that list 4, 5, and 6, this was scenario 2. List 5 is my observed values. List 6 is my expected values. So I'm going to go to stat, tests. I know it's towards the end. Goodness of fit. Now this is going to be list 5 and list 6. And let me come up here. And so I'll hit program, go down to chi-squared goodness of fit. Okay, the observed list, again, I set it up the same. So list 5, expected values, list 6. Okay, enter, calculate. And you see we get the same values of 23.4, 23.4, 2.83 times 10 to the negative 4. We get that on both calculators. With the NumWorks, so let me go back a couple steps. Now all I need to do is just go back into here and change this one to 22.5. See, I kind of wish that they would link this function to, X1, Y1, and all that stuff. But they haven't. and maybe that'll happen on a future release. I don't know, but this is how we deal with it. All right, so 22.5 and 4.5 everywhere else. Still 5 degrees of freedom, 5% significance level. Okay, and there's our 23.4 and our 2.83 times 10 to the negative 4. All right. So you can see that with these two different scenarios, we end up with two different test statistics and we end up with two different p-values. All right. Now let's go ahead and keep moving forward. Now we have our test statistic, but we're going to need a critical value to compare it against, right? So in order to get the critical value, okay, we have our test statistic for each one, right? The test statistic on the first scenario was 14.07. The test statistic on scenario 2 was 23.4. Okay, what we need is this critical value. So yeah, I'm, kind of showing you the answer we're going to get, but let me show you how I got this 11.07. So we're going to need to convert the significance level into this critical value. All right, now on the Texas Instruments calculator, there isn't an inverse chi-squared function. So if we go to the distribution functions, this is the newest model Texas Instruments. You can see we have a chi-squared PDF, we have a chi-squared CDF, but we don't have an inverse chi-squared, right? There's inverse norm and inverse t, but there isn't an inverse chi-squared. So instead, this is the same for you TI 83 people. I wrote a program called inverse chi-squared, okay, where you put in your significance level, you put in the degrees of freedom, and it'll chew on it and it'll spit out a critical value. Okay. This will work exactly the same on a Texas Instruments 83. On the NumWorks calculator, let me exit out of this. So I'm just going to hit home. Now it does have that inverse function built in. So if we go to the distributions app, click OK, we can go down to chi-squared. Degrees of freedom is 5. Okay, now we want the area to the right, because this is the area in the right tail. And we have an area of 5%, our significance level. And we hit execute. And you can see we get 11.705. So it's kind of rounding right there. Okay, so this is how we got the critical value of 11.07. So we have our critical value of 11.07 for scenario 1. And remember, this divides the reject the null region and the fail to reject the null region. Over here in scenario 2, 11.07 does the same thing. Reject the null, fail to reject. And then we just look and see how the test statistic compares to the critical value. So here the test statistic is greater than the critical value. So that's clearly in the reject the null region. And on this second scenario, our test statistic is way larger than our critical value. So yeah, we're going to reject the null here too. If you compare p-values, here you can see the p-value is smaller than the significance level. So if p is smaller, reject the nuller. Over here, with the test statistic this big, we have a p-value that's really small. So here the p-value is smaller than our significance level. So if p is smaller, reject the nuller. Okay, and the null hypothesis was our original claim. So now we can use our conclusion table. We are rejecting the null, and the null was our original claim. So there is sufficient evidence to support rejection of the claim that the six-sided die is fair. Right? Our claim was that it was fair, and we have enough evidence to reject that claim, that it's not fair. And you remember, we could kind of see that, right? If this was a fair die, then our observed values should have been equal to all of these expected values. All of these expected values should have been the same, but they weren't. So we kind of saw early on that this was not fair. But now we can say that it's statistically true, okay, that it's not fair. There's enough evidence to reject the claim that it's fair. Now, this second scenario, okay, was okay, it's not fair, it's an unfair die, but it's unfair in a specific way. So what we did show is there is sufficient evidence to support rejection of the claim that the die is unfair, uh, given this particular distribution of probabilities, right? So again, up here on this scenario, we're claiming that it's unfair, the probabilities are unequal, and we can see that the observed values, it looks like it's unequal. It's just not unequal this way, right? Because a one on the die occurred 13 times. It should have been almost double that. And a 3 should have occurred with an equal frequency as 2, 4, 5, and 6, but it didn't. It occurred like almost twice as much as a lot of the other numbers. So our die is unfair. It's just not unfair that way. So our claim was it's unfair in this specific way. And what we found out is that no, it's not unfair in that way. So in scenario 1, the distribution that would result from each six-sided die outcome having equal probability was tested. And in scenario 2, the distribution was tested. And in the end, scenario 1 showed the die is an unfair die. Scenario 2 tested a possible unfair scenario, but it turned out to be the incorrect one. So as stated from the beginning, one would normally not perform two tests in parallel, but I wanted to show both the observed and expected tables side by side. So two setups, one where we have a uniform distribution where the probabilities are equal versus a non-uniform distribution where the probabilities are unequal, side by side, so that they could be compared by you, the student. Okay. So rather than just do two separate, examples, I thought I could do them side by side and help you understand what we meant by uniform and non-uniform. And this is the formula you use if it's expected. This is the formula you use if it's expected under this kind of non-uniform probability. Okay. I think maybe the very last thing is we kind of jumped through these extra hoops to get this critical value, but let me see here. The NumWorks calculator, I think, when we've done inference, I think if we click next, it's going to show this picture. Okay. So remember, this was the case where the claim was that it was an unfair die, and it was unfair with a probability of 1 being 50%. So this shaded area is showing the significance level. Remember, it was 11.07, right? You can see it's right about at 11. But this p-value is so small, it's way off to the side. Okay, we can't see it. It's at 23.4. Let me back up and let me see if I can make it show up. If I put 7.5 here, right? This was scenario 1. Okay. Okay. Okay, we get a different test statistic here. Okay, so here you can see this is the critical value at 1107. This is an area of 0.05. That is the significance level area. And the p-value was 14, right? Between 12 and 16. It was 14, and the p-value is this orange area here. So you can see that the p-value is smaller than the significance level. So if p is smaller, reject the nuller. And you can imagine if this is the critical value here, off to the right is the reject the null. And our test statistic is right here. See, it says chi-squared. This is our test statistic. It's in the reject the null region. Okay. So yeah, the numworks is a little clunkier to work with, but it also is a little more visual. So I kind of like that too. All right. So I think that's a full explanation of what we're doing here in this section. Um, I've printed all this out, screenshotted it, so you can kind of go back over this yourself. And the next one, I think, is a think, pair, share. Give that a shot and see if you can do it all from beginning to end. Okay, let me know if you have any questions.